membrane does is surrounds the mitochondria or surrounds the ribosome. You know, it controls what's passing back and forth. So when you and that's why we spend so much time discussing the cell membrane, because it covers for all the membranes. I ain't got to discuss each one separately. When I get the cell membrane real good, then what I've said for it applies to the elements too. It works pretty well that way. And so all these structures have to have a way to get things inside them. And however the cell membrane does it, those do it the same way. Now the cell membrane is a double membrane. And some of the organelles, like the lysosomes, have a single membrane. Some have a double membrane, like the mitochondria. But regardless of how many layers, the function is synonymous with the cell membrane. And remember now, if you are a prokaryote, you're a cell, but all the stuff a cell has does not packaged in membranes and those other structures. It's just all thrown in there together. Very primitive, but very effective. Okay? Next slide. Fluid mosaic is a word we use a whole lot. Most folks have no clue what that means. If you look at, if you're going to retile your bathroom or retile some part of your house, if you look at the tiles, most often they're not all the same texture on different colors, blocks here and there. That's a mosaic. If you look at a cell membrane, you look at it's not all the same stuff. There's different things scattered around. That's the mosaic impact. The proteins are scattered around. Like if this table here is a surface, then there'd be a protein here and one here and one here and one here. Because the only way to get through this membrane was to pass through that protein, which is the door opens and closes. You can't pass through anywhere else but that. Now, there's some words on there, glycoproteins. Any word glyco means carbohydrate. So if you have a glycoprotein, you got some critter there that's half protein, half carbohydrate. You think glycolipid is? It's half carbohydrate and lipid. The cholesterols are all fat. They're total fat. And there's nothing in the word to give you that clue. You just got to know it's fat. But so are steroids. Now, those glycoproteins and glycolipids that stick off, they have functions they perform within that cell. The glycoproteins are your name tags. That's how one cell recognizes another cell as being part of the family. And a bacterium invades your body. Their glycoproteins, you don't recognize those. You go, whoa, there's a foreigner. And unlike our country, you don't like foreigners. You kill those suckers. And your immune system, when it sees the glycoproteins, which we call antigens, starts making antibodies. And any cell with that particular glycoprotein, that antibody will kill. And you don't get sick. You don't, and even viruses have it. Problem with viruses, though, they're not alive, so how do you kill something not alive? You can't kill it, but you can disrupt its mechanism. All a virus does is hijack your cells and then make your cells make baby viruses. And those viruses escape and they infect more of your cells. And you go to bed feeling all right, you wake up in the morning feeling sick. It happens overnight. They multiply so fast. But your antibodies, you don't have a cold forever, do you? You're going to get well eventually. So you can take care of a virus. It's a very slow process. And all you do is you disrupt that virus's mechanism so it can no longer invade your cell and take it over. You don't kill it, you just tie its hands back. And that's how you get well. But when you look at a cell membrane, some books have it drawn very simple, which I don't like. It's just too simple. But the mosaic tells you a lot of stuff in that cell membrane. Now, I almost said cell wall. I got to be careful doing that because animals do not ever have a cell wall.
Isn't that plants?
Only plants do. That's how a plant. If you stack up cardboard boxes, right? Well, the cardboard is the cell wall that holds your stack up. Well, those trees, they don't have any bones inside them. It's just that stack of cells. And what happens to make a house plant wilt? What happens to it if it wilts and droops over the bulb? What have you not been doing? Watering it. The only way to make that plant stand up is to fill those cells with water, like you blow up a balloon, which you do now. If you don't, when that water's all gone, the plant just falls over and it wilts. Now, some folks use that as a guide to when to water it. That ain't healthy for the plant. For a long, your plant won't snap back. You should water the plant before it shows signs of getting water. And a lot of times, some folks just don't know how to care for a plant. And the worst thing to do is put the plant out of your eyesight so you can't see it. So you'll forget about it. Come back in a week's time and go, oh man, I forgot that plant. And the leaves are brown. Fell over. If they could talk, it'd be screaming. But if you put it where you're sitting, like in your bathroom, in your kitchen window, you'll be more inclined to add water to it now and then and keep it. And those violets, African violets, you got to really take care of them suckers. The coleus plants, they're pretty durable. Yes.
Do plants have cell walls?
All plants have cell walls.
But the animals don't.
They do not. We have bones, and we're very soft. You grab that tree limb, ain't no soft to it. It's just hard. But that's called cell wall. Oh, now bacteria, they have cell walls too. Bacteria have cell walls, which is a plant-like trait in those bacteria. Your algae, they have cell walls, but they also make their own food. Okay?
They make a lot of mess.
This is a picture that I found, and it shows a lot of stuff going on. Now it's time maybe to snap your picture. That's all right. Get close. Get right on. That is a cell membrane. And once you get your pictures now, I'll tell you what we're seeing here. All right. Do you see the little red marbles, I think orange marbles? That's glyco. All right. If you come from a protein like this, you're a glycoprotein. This is just a protein. What's trans mean? To go through. This goes all the way through. Can y'all see that opening right there?
To the membrane.
This is a hollow tube, and like a big straw, things can pass through this tunnel and come out in here. No tube here, tube there. This is a protein receptor. And though it doesn't say it, this is a protein channel. They're both proteins. Now, if you just have the glycose sticking out of these blue things, that would be your glycolipid. The blue things are your phospholipids. All the blue cannonballs are the phospholipids. You see the legs hanging off of them? All these blue things have two skinny legs. And the skinny legs hate water. But the blue heads love water. There's water outside a cell, and there's water inside a cell. So the way it's arranged, these blue things are always facing the water because they love it. And the tails get as far away as they can from the water. That guarantees you have this two-layer arrangement. What would it look like, you reckon, if the blue parts hated the water and the feet loved the water? It'd be hairy looking, wouldn't it?
Yeah.
All the feet be sticking out, and the two heads be side by side. But that's not the way it is. In this phospholipid, the legs of it, they flat do not like water, which is out here. The heads love the water. Therefore, they're always going to be facing the water, but the inside or outside. And the legs are as far away as they can get. That puts them inside the double leg. Now, can water dissolve fat and vice versa?
No.
No. So the reason water stays out here because it can't go through the fat. The only way things can pass back and forth is through this tunnel right here. That's the door. Now, these yellow things you see right there, that's that good cholesterol, the stuff you need. There's good and bad, right?
Yeah.
Now, the good cholesterol you find doing their part and makes yourself better. Where do you find the bad cholesterol in your body? Where is it found at? Inside what? Inside your blood vessels. They'll stick to the walls of blood vessels, and when it was that big, after a while it's this big, there's this big, there's that big, and next thing you know, blood can't go through it. And you have heart disease. So and you have good cholesterol, which is HDL, and I think of happy. And you have LDL, which will lay you low. That's Bobby Tell. I mean, that's how I remember it. HDL, actually what it really means is high density lipoprotein. And the LDL means low density lipoprotein. Now here's the trick. You got your thing of water here. Water density is 1. Okay? If the thing up here, density is more than 1, it'll sink in water. Okay? If it's higher than 1, it'll float in water. Well, the good stuff you see there will float in water and not stick to your cells. The low density will go and stick to your cells and stick more and stick. And next thing you know, it's so clogged up, blood can't go through it. The high density cholesterol you want to have. The low density cholesterol you don't want to have. You need cholesterol. So don't think cholesterol is bad. It's just you don't want the wrong kind of cholesterol. And right there you see it being used all over that cell membrane to give it strength. These things right here are held together by this. This is your strengthening agent to keep that membrane strong. And all these things sticking out, that's how one cell identifies another cell as being part of the family or not part. Yes, ma'am.
Can you explain the transmembrane protein one time?
Transmembrane, trans means to go all the way across. That protein goes all the way across. It goes one side, that's how things, for example, a hormone will land right there. Like, ring a doorbell, ding dong. Well, then inside here, something will happen. That cell might make insulin. If you're a rattlesnake, it might make poison that you're going to bite the rabbit and poison the rabbit with. It might make even more cells.
And the one with the hole in it.
And the one with a hole in it, that lets like glucose go right on through and go into the cell. Glucose, is, though it's small, it can't go through here, but it can go right down through yonder.
So it's a chamber.
It's a chamber. It's a tunnel.
Are both of them chambers? Or
No.
just the one with the hole?
This is not, if you see us down here, this down here produces ATP to make something happen. You don't see one here, do you?
No.
Because he's not a doer. He has no function other than to provide a way to get in.
So you have like the workers and then the transport.
Exactly. And I would call him the worker, him the transporter. You need both of them now. You need both of them. And you have, now, I see 2 right there. Oh, you have a lot more than 2. You have a lot of them. And the opening in this one right here, it can close and it can open. So that's the opening. That proteins are the only compounds that can change their shape. They can swell up. Now, if you can't get bigger this way, and you swell up, you're going to get bigger toward it, and you're going to close that channel off and keep things out. So he can change it. You ever heard something called denature or something?
Yeah.
When you cook your food, you are destroying the proteins because the heat makes them change their shape, and that makes your meat tender. If you don't cook it long enough, you find that your roast doesn't fall apart like you like it to. You know, like it doesn't fall off right off. Just I can't pick it up, it falls off because the heat destroys these organic compounds. But the cell membrane is, now we didn't know about this until I guess around the 40s, 50s. We didn't have an electron microscope. The ones we have upstairs can't see this. I can see a line, but I can't see what the line is made of. Actually, 2 little layers, really and truly. But the electron scope shows it beautifully. I mean, you ain't got to imagine it, you'll see it. All right. That's the thing I want to show you?
Yeah.
Oh, it's on there. Is it on your paper towel too? That's stupid. Well, I'm going to take it off. No, then my numbers are messed up. Just refer back number 5. But you can fill it in. I didn't know it was on there twice, frankly. I'm surprised to see it twice. I must have liked it. But if you have number 6, you got number 5, right? I'm moving on then.
That's it, right?
Oh, there's twice too, okay. Now we're on a new thing. Alright. I've done talked about this with those tails hating water. So go ahead and get your blanket filled in, and I'm going to tell you what the real words are for hating water and loving water. There's words we use for it. I'm going to look at just a minute. Okay, there. Yeah, I can show you the next slide while I show you.
Some of those you got red on there, you don't have it on this too.
Which one's on yours is not red?
Out.
Hydrogen.
Hydrogen.
You mean right here is black? All right.
I mean, you got it red there, but you got it black on here.
I want to make it same as there.
This is the same one with 6.
Oh, it's under this thing here. I can't get to it. Well, I'll have to leave it alone because I can't get that off of it. I know what you mean though. Don't worry about it. But I won't change it now because I got a picture there on top of all this stuff that'll come on later on. I need to stop doing that so I can get to it and fix it without having a picture messing me up. Now you do realize that even see that thing 2 right there? That might be the answer to a question one day. It's not red though, is it? I mean, I'll have the rest of it make you kind of look for it. But the red things are not my answers. Hope you know that by now. It's just the way it guides you through the power plant. So I'll use that too up there. For how many phospholipid layers are there? The answer is 2. I ain't read. But I'll ask you that question. Now, polar and non-polar, you know how those things work where you have one Higgs electron becomes negative in the face of that. Well, on those 2 layers, those legs I showed you, those are fatty acids. Fats do not like water. And we call that hydrophobia, like a phobia. You're afraid of something. So those tails get as far away as they can from the water, and that puts them right inside the membrane. Now those heads, those blue-looking cannonball heads, but those love the water, and we call that hydrophilic. So if you're hydrophilic, you love the water. What would you call a cat? Phobic or philic? What do you call a hound dog? I have dogs. You can't get out of the water. Cats, though, you got to throw that sucker in. He ain't getting it by itself. But I've had dogs that hop in the water and just don't think twice about it. So a dog would be, in my mind, kind of hydrophilic. And a cat, he ain't getting that water if he can help it. Maybe hydrophobic. What is the other name for rabies? Hydrophobia. Did you know that?
No.
A person with rabies is not afraid of water, he dislikes water. And rabies is called hydrophobia. But this hydrophobic is not anything to do with a disease called rabies. Except for the fact that neither one tends to enjoy water. Alright? And those little black cannonballs, they actually attach themselves to the water around them, or those hydrogen bonds. You know, water loves those hydrogen bonds. But inside the water is a covalent bond. But when water hooks to each other, or to the cell membrane, hydrogen. And how hard is it to break a hydrogen bond? Hard or easy?
Hard.
It's easy. It's easy. So it's kind of stuck to it. It ain't like super glue. Now, this picture came up as one of the popular writings. This is another rendition of what I showed you earlier without the mosaic stuff. It's just, I want to show you that this here is what's called, these are the phospholipids. This part is the phosphorus. And phosphorus likes water. This is the lipid part. And lipid does not like water. The water is outside here and outside there. That's going to put these legs as far away as they can get. That means they're inside. But the heads, they love the water. They're going to be outside trying to get all they can. That guarantees you that that shape will be true always. And the picture here, this is one of the 2 phospholipid layers. That's the other one. And now the heads are red. They love the water, which is here. They're going to be against it. These love the water inside the cell. The legs hate the water. They're going to be as far away as they can get. And the cholesterol inside here gives this thing strength, so you can't just... Oh, it moves. These things can move around. Even though they're moving, the head stays facing the water. And those cells, they stay inside. But they're moving. It's not glued down.
What's inside? Air?
It's a kind of a, I want to say colloid. It's not air. It's a colloid. And a colloid, those tails have no problem with the colloid. They flat don't like the water, and that makes sure they stay sticking in that colloid. Mayonnaise is a colloid. Because if it sits, you soon see it got stirred a little bit. But no, it's not air. It's not air. That's for a fact. Okay? As a matter of fact, There's not as much space as you think it is by the picture. There's not that spacing, really. We draw it that way because we can. All right? I tell you, those heads are not glued together. They kind of move around. Even though the head stays facing out, they can move.
So what makes it float through things if there's not air in it?
Huh? All liquids are not water. All liquids are not water. And there's liquid in there, which is that colloid liquid, which the tails have no problem with. But the tails can't spin around because there's water outside, and they won't go there. That makes the tails always face
I
inside.
understand why it doesn't mix with it, but what makes it
What's
float?
one now?
I understand why it doesn't mix with it, with the water, but what makes it float outside of it? Like, for example, through blood, it just
Well,
floats
first
until it
off,
attaches to the wall.
This whole cell membrane is hooked to you all the way around, right?
Mhm.
So it's always continuous. And the cholesterol inside there prevents it from just dissolving away and going away. Even though it's moving to some degree. It ain't going to just, like if you put soda crackers in water, it's going to totally dissolve. The thing about animals that live up north have a unique thing with their legs they can do. And the caribou, the first time we saw it, a caribou can cut off the circulation to his legs and therefore save his heat and not freeze to death. We can't do that. But the animals who live in the environments freezing cold, nature has a way for them to get through the environment. And I think moose do it too. I know caribou do. And all they're talking about, you ever see the caribou's legs, how long and skinny they are? It's just like 2 sticks, like 4 sticks. Well, if blood went down there, it wouldn't take very hard for the blood to lose heat. Animal heat from the body. He'd freeze to death. And so that's why you find that the lower legs, they can reduce circulation. He's big up here. Sometimes take a look at a moose's legs. You wonder, how do they hold the big old body up there so skinny? Because they got to be, because you don't want to lose all that heat and perish in wintertime. If I ain't mistaken, we tried to give caribou hay. They want to eat it. We had folks who said, let's feed the caribou. They were caught in a snowstorm, and they couldn't migrate, and they were dying because the snow covered it. So they dumped out hay. And cow eat hay, but caribou won't do it. It's not a natural forage for them. So though he had all the food around there, they still kept dying. I reckon sometimes you just can't mess with nature. When she's time to erase his specimen, she does. Here's being unsaturated is pretty important.
Eat.
In here, unsaturated fats and saturated fats. Which ones do you want to eat? The unsaturated or saturated?
Unsaturated.
Unsaturated. That's vegetables. Those caribou, the fatty acids in those cells in their legs contain unsaturated fats. That makes them retain, they're more fluid, they can move more. They don't lock down and kill the animal. The ground squirrel is one that I didn't know about. I did some reading on it, and sure enough, that bad boy, in real cold weather, where there's ice storms and trees breaking over, they survive pretty well.
True.
The ground squirrels that live in trees, the big old tree rats. But because the phospholipids of the brains contain the unsaturated fat, that makes them more fluid. If you remain your fluidity, then oxygen can still pass through the cell membrane, and feed that cell. When you lose that fluidity, oxygen cannot pass through, and that cell dies. If it's a brain cell, that poor squirrel ain't got long through this world. I mean, squirrels they're helpless, but nature takes care of her own, it looks like. And I found, but I got the feeling there are a lot more examples where animals in harsh conditions have some, and you couldn't do that. If you get caught out in the weather like that, you're going to probably die. So again, squirrel. I mean, you ever seen, I often wonder how these things survive year to year, because I know it gets freezing for days on end, and here they are in the summertime, they're back eating your bird feed and all kinds of stuff, tearing your feeders up. But that, if that layer can remain fluid, that's an advantage. And if those phospholipids contain unsaturated lipids, that's an advantage. If you eat too much meat, is that good or bad for you? Bad for you, because the meat products are saturated fats. That's not what you want to use to build those cells, those cell membranes. I mean, I'm the world's worst vegetarian, but I know it's better for me. I mean, I know it's better, but I still like to do a juicy steak down there. My wife, really, she eats salmon, but she sits down and has 3 vegetables, and that's all, and she has no meat, no bread. And when she cooks that way, and I don't mind it, but I still like a good old pork chop down there, or something like that, too. I told my wife one time that, see, they're called canines. Canines are for meat eaters. Honey, I'm a meat eater, so when you cook my mashed taters, cook me some cube steak with it. So usually in the kitchen, we're both cooking. And we get each other way, of course. This is showing you the difference in the fluid nature. See how these things can move, but not with cholesterol. Cholesterol interferes with their moving action. They go back and forth. This is not often common because that's going to make the things break apart. But this would be unsaturated fats, and these move a lot more, which is good for you, than these. These are saturated, and they're just at a tension. They don't budge. You get these fats from plants, and these fats from animals, and that's why they always say that the vegetarian diet. And I agree with them. I can't say no. It is the best diet around. I know Hawaiians and Polynesians live for a long time because they have a fruit vegetable diet. And then we got there and we moved and opened up Pearl Harbor. We brought in steaks and things, and they began to have diseases because the diet changed. So there's no doubt in my mind that vegetarian diet is the best diet in the world. And the cholesterol, we just make sure they can't move much. If you get a splinter, you're trying to get the thing out, and you try and tear your skin a little bigger to get to it, don't worry. And skin's real tough and don't want to tear. Right there's the reason. So, and this can change as time passes inside your own body. I've told you this one already in a way. Let me ask you a question. If you're water soluble, can you pass through fat too? No. If you like water, then fat's opposed to. And the things you eat, all the carbohydrates, the proteins, things like that, those are water soluble. On the other hand, they won't go through fat. They can't go through. They just cannot. They can't just go through here, because this is fat. If you're water soluble, I can dissolve in water, but I don't dissolve in fat. Nothing goes both ways. You can't find it. There's nothing in the world that's both fat soluble and water soluble too. You're one or you're the other. If you dissolve in water, you can't dissolve in fat. If you can in fat, then you can't in water. That's how the body works. Steroids. They are fat. So can they dissolve in fat? Absolutely. They are fat. They go right into a cell. They don't go through a channel because they themselves are fat. They can dissolve in fat. Go right on through the cell, get inside there, go to the nucleus. But a non-steroid is water soluble. He can't go in except through that tunnel, or he lands on that long old protein and rings the doorbell and hope that they hear him and inside do something that he wants. He can't go in there because those phospholipids, their whole thing is, if you are water soluble, you ain't going through me. If you're fat soluble, come on. But if you're water soluble, then what you see there won't let you in. So the fact that the layer of a cell is fat, that keeps out water, and it keeps anything that can dissolve in water. That controls what comes and goes. I mentioned the proteins. If you're water soluble, that's how you got to get in. You got to go through a protein to get in. Because you're not going to go through that cell membrane. You got to pass through a protein. Lipids, because they are fat, they don't need that protein. They go right through the, fat can mix with fat, right? But they go right through the cell membrane, go right in. That's why steroids are so powerful. They don't wait outside. They go into the cell and they get the job done. Like those saying, if you want it done right, do it yourself. That's what they do. They do it themselves. Now you saw this in the picture earlier. There are two kinds of proteins. Some are tied down and some can move around because the membrane itself moves around. That door there ain't going to move. It's always going to be right there, right? If this wall were such that there was ball bearings and pulleys, you can slide that door here and put it where you want it. So you have one kind of a setup where the protein door cannot move. It is actually in place. Another kind where you can move the door to where the stuff is. Instead of moving the stuff, you slide that door over there. That's two kinds of proteins based on whether the protein can move or not move. There's a lot of proteins in the cell. But if you have a carbohydrate hooked to it, that's that glyco portion. Glyco means carbohydrate. They should call it a carboprotein, but they don't do it. I'd call it carboprotein to be done with it, but they call it glycoprotein. And there are a lot of proteins that the glyco can be hooked to. Here's some proteins. Look ahead just a minute. Good, I got a picture. Now you got to try to describe it to you. The word adhere is derivative of adhesion. When you take things together, they adhere to each other, they stick together. And you feel your skin? These cells, they're hooked this way to each other. They're hooked together. Your skin's hooked together by these adhesion proteins. And my next picture will show you. It's like they're kissing each other, but instead they're actually stuck. And there's a word called cytoskeleton, extracellular matrix. Have you ever seen them pour concrete and put wire in concrete first? Well, that'd be the cytoskeleton. And that wire is what makes the concrete not break. Concrete can't hold its own weight up. It'll break in a minute. But the wire inside it gives it added strength. So your car can drive across it and hopefully not break the corners off, but sometimes it break off anyway. Picture I'm going to show you is this one. In this case, here are two cells. One goes this way, one goes that way, and they're stuck together. These are the glue. They're sure not there. There's the glue that holds those two cells side by side. Those are adhesion proteins. And over here, inside the cell you have the cytoskeleton. Outside you have collagen. And this thing makes it all stick together so it gives you strength. So there's two ways you use it. I can use the adhesion protein to hold the wiring together inside a cell. Or I can use it to make two cells remain stuck side by side. When you cook meat and you heat it, you destroy the adhesion molecules and that just pulls it apart so tenderly. You don't heat it enough, or heat it too much, it's salt time. Here you go. Table shakes all right. But if you cook it, as you know, like Grandma was cooking just right, give me a fork, it just pulls apart. Because the molecules, the heat destroys them. And they lose adhesion, and it makes the cells separate, and we call that tender. And some tenderizer you put on, some chemicals can also do it. But you still cook it though. If you cook a hamburger, well, you cook a steak outside or a pork chop, you put on the tenderizer. I even take a fork and stick holes into it. So I get stuff good inside there. And if you do it right, it won't taste like you got to tear it apart with your teeth get into it. But the heat will destroy those proteins. If you destroy the proteins, then you will free up the adhesion molecules, and your meat just falls apart. It's just so tender. Some proteins are not adhesion. Some proteins are communication proteins. They're designed to talk and all stick cells together. And we'll show the picture in this about last one because time's about up already. I might even have a picture showing you those gap junctions. The only place you find those discs are in your heart. And they stand out so well that it's often a giveaway for identifying tissue. If you see those discs, you know it's heart tissue. But where one cell butts to another cell, that's a gap junction. There's also adhesion molecules there, but this cell can talk to that cell through those communications. The picture I have is that. Notice how something can pass all the way through both cells. They line up. perfectly to pass through not one cell, but both of them. So a molecule actually can move from
Coordinated.
one cell into another cell by going through these communication proteins. One by itself is a protein channel. Two of them line up like that. They're both protein channels. But they line up perfectly so I can just keep on going from one cell into another cell. And then maybe into another cell. We'll come in, we'll start this slide tomorrow.
Can you
We'll be
go?
on slide 619.
Can you
So
go
I'll make
back?
notes of myself, and I'll grade these papers you'll have done today and put those on Angel tonight. And we are done.
Can you go back to number 4 for me?
You mean the number 4?
Uh-huh.
That one?
Yes, please.
Okay. If you have papers, come and get them.
Oh, thank you.
Oh, Lord. That'll break your foot.